Glass breaks. It always has. For thousands of years, we've accepted this truth. Drop it, it shatters. Hit it, it cracks. Bend it, it snaps in half. Every single time. Until now. This glass bends, and it never breaks. Welcome to the impossible factory. Let me show you exactly how we do it. The process begins with ultra-pure silica sand, refined to 99.99% purity. Any impurities would create weak points in the final product. Next, we add proprietary polymer compounds. These molecules are the key to flexibility. Each batch is measured to the microgram for perfect consistency. The materials are mixed at the molecular level. Silica particles bond with polymer chains, creating a hybrid matrix that behaves like both glass and rubber. This mixture is heated to 2,800 degrees Fahrenheit. At this temperature, everything liquefies completely. The furnace glows orange from the intense heat inside. The molten material is floated on a bath of liquid tin. Tin is perfectly flat at the molecular level. This creates glass with flawless, optical-grade smoothness. The glass then enters a 300-foot annealing tunnel. It takes 45 minutes to cool gradually. Slow cooling prevents internal stress that would cause cracking. Now comes the critical step. Robotic arms stretch the glass in 4 directions simultaneously. This aligns the polymer chains into a flexible matrix. The stretched glass is exposed to intense ultraviolet radiation. The UV light permanently locks the molecular structure in place. The flexibility is now built into the material itself. Every sheet undergoes rigorous flexibility testing. First, it's bent to 90 degrees, then 180 degrees. The glass folds completely back on itself without any damage. Impact testing comes next. A steel hammer strikes the glass with 400 joules of force. The glass flexes deeply, absorbing the impact, then springs back to flat, completely intact. Drop tests simulate real-world accidents. Panels are dropped from 50 feet onto concrete. They hit at over 50 miles per hour. They bounce. They don't break. Laser scanners examine every millimeter of the surface. They detect flaws smaller than a human hair. Only perfect panels move to the next stage. The glass is coated with nano-ceramic particles. These particles are just 3 nanometers in diameter. That's 1/30,000th the width of a human hair. The coating creates a molecular bond with the glass surface. This makes the glass hydrophobic and self-cleaning. Water beads up and rolls off instantly, taking dirt with it. The coated glass is heat treated to 800 degrees. This permanently fuses the coating to the surface. The bond is now stronger than the glass itself. Now the glass can be cut to any size or shape. High-powered lasers slice through with micrometer precision. Cuts are accurate to within 1/100th of a millimeter. The edges are polished to optical quality. Diamond wheels create surfaces smooth enough for telescopes. Every edge is beveled and inspected. The glass can be molded into complex 3-dimensional curves. Traditional glass could never achieve these shapes. Robotic presses form sweeping architectural curves. Here's something remarkable. This glass can actually be rolled up like fabric. Imagine rolling up a window and putting it in your pocket. But can it handle extreme stress? Watch as we twist this panel 720 degrees. That's 2 complete rotations. The glass spirals, but never cracks. Compression testing pushes the limits even further. A hydraulic press applies 10 tons of force. That's equal to the weight of 2 adult elephants. The glass compresses, then springs back perfectly. Thermal shock testing is particularly brutal. The glass goes from -320 degrees Fahrenheit to 500 degrees in seconds. That's an 820-degree temperature swing. Normal glass would explode from the stress. We even test ballistic resistance. High-velocity projectiles are fired at the panels. The glass catches bullets that would shatter conventional glass. So where does this impossible glass go? It's being installed in the world's tallest skyscrapers. Entire buildings wrapped in flowing, curved glass facades. Architects can now design shapes that were impossible before. Buildings that curve like waves. Structures that seem to defy the laws of physics. The automotive industry has taken notice. Next-generation vehicles use this glass for windshields. These windshields survive crashes that would destroy normal glass. In accident tests, the glass protects passengers better than ever. It flexes on impact, absorbing energy instead of shattering. No sharp fragments. No injuries from broken glass. You probably have this technology in your pocket right now. Modern foldable smartphones use flexible glass screens. The screen bends thousands of times without failing. Drop your phone? No problem. This glass has been tested with hundreds of drops. It keeps working when conventional glass would have shattered on the first fall. This technology enables entirely new categories of products: rollable tablets, bendable e-readers, flexible displays, devices that were pure science fiction just 5 years ago. The factory produces thousands of panels every single day. They're shipped to 70 countries around the world, from architectural projects to consumer electronics. This is glass that bends reality itself. It challenges everything we thought we knew about materials, breaking the fundamental rules without ever actually breaking. This is the impossible factory, where we take the word impossible and we prove it wrong. What should we make impossible next?